And so we'll really discuss molecular symmetry and the transition dipole moment integrals today. We'll review a little bit about the point group of CI, the particle in a box, and then we will get into water and some three-dimensional systems. And we'll talk about Raman. So we've talked about direct absorption and emission, which uses one photon. Today we're going to get into scattering. So we'll learn about what happens with two photons and Rayleigh scattering and Raman scattering. So that'll be the sort of the top of the mountain today. So we've gone through the need for symmetry, the things that it does for us. We start with the Lewis dot structure. We did that in lab. We get the point group. We really focused on the character table last time and identifying the Millikan notations. We'll stop and do a Kahoot, if I remember, about midway, and then we'll look at the direct product tables today. So this really completes the whole thing for this course, is coming up with those selection rules for spectroscopy using the direct product tables, which we can't use unless we know the point group and the Millikan notations. So. What we're representing with these Millikan notations is the wave functions. Now, we've talked about the degrees of freedom. There's translational motion, rotational motion, vibrational motion, and then there's also the electron cloud, the electronic wave functions. And the total wave function is the product of all of those. So if you have any odd wave function in that product, it makes the whole wave function odd. And if all of them are even, then the whole wave function is even. So when we talk about direct products, even within the wave function, the total wave function, it's the direct product of all of those individual pieces. Now, when we talk about direct product, you'll get experience with this in a couple of weeks when we do the Excel version of what you did in Calculus Week. But a direct product of two functions, let's just, let me flip to the board. Go here. So when we have wave function 1 times wave function 2 using this direct product operator, if we were to look at this in Excel, we have minus L over 2 down to L over 2. And wave function 1 has a bunch of numbers. And wave function 2 has a bunch of numbers. And the direct product is just this number times this number equals a new number. So it's just this piece times that piece. So every little number in that wave function is multiplied by the corresponding number at the same coordinate. And so it's just two vectors times each other. Individual pieces of those vectors are multiplied by each other. And that's what we mean by direct product. So you can imagine if this is symmetric, I'll draw these wave functions on their side, right? So this is the particle in a box wave functions, right? So we have some plus there, this whole thing is plus, and this piece is minus. So right here, these numbers are all plus, and then down here, these are all minus. You can see that even times odd is odd. And so you can kind of see the symmetry of those wave functions. I've drawn them in sort of sketch format, but that's what you would see in Excel. You would see wave function 2, the top half of that column is positive numbers, the bottom half is negative numbers. And when you multiply column 1 times column 2, you get column 3, where the top half is positive, the bottom half is negative. And so even times odd is odd. Now, for the total wave function that we saw before, we had translational wave function, rotational, vibrational, and electronic give you the total. And so it's all of those numbers times each other. If they're all even, then the total will be even.
So what if it's odd times odd? Would that be even?
Yes. Mm-hmm. Yeah, so odd times odd is even, and even times even is even. So you can really kind of think of this odd and even not like our traditional odd numbers, meaning it's divisible by 2 or not, but more like plus 1 or minus 1. So positive or negative. So that's what really we mean by even and odd. We're looking around the origin and seeing if the left and the right side have the same sign or different signs. Okay. And so we talk about direct products all the time, but mentally I want you to kind of think it's just columns times columns. Okay. And so let's look at these integrals and the selection rules. We've covered this a little bit before. So we know that the intensity of a spectroscopic transition is proportional to that transition moment. In direct absorption and emission, it's the dipole moment. In Raman scattering, it's the polarizability. So we would just use the most generic term would be the transition moment integral. If you're just dealing with absorption and emission, it would be the transition dipole moment. So you'll hear me use those kind of interchangeably. They're exactly, transition moment is a more broad umbrella. Transition dipole moment is just absorption and emission. But anyway, that integral result squared is proportional to the intensity. And so if you can demonstrate that that integral is 0, then you know that that transition is forbidden. So if the results of the direct product does not contain the totally symmetric, irreducible representation, that's the top row in the character table, then this integral is 0. And that spectral intensity is 0. And so we say that that transition from n to n prime is forbidden by symmetry. This explains the simplicity of molecular spectra. There's a whole lot of transitions that theoretically could occur, but because the symmetry makes them forbidden, they don't absorb light. So we might have seen just a continuum of spectral lines, but a lot of those have dropped out because of symmetry, and therefore we see this fairly simple and understandable spectroscopic transition. So this is starred up here, but not only is it starred, I've created a whole new slide just to emphasize that. Let me repeat. If the result of the direct product does not contain the totally symmetric, irreducible representation, that's the top row of the character table, then that transition is forbidden by symmetry. Just pay attention to those little stars in my notes. And we're going to get practice doing this today. So we're going to come up with the direct products of the wave function. So you'll understand what that top piece means by doing it. Okay. All right, I see people writing. Okay, so now let's use that direct product table. So we use Vesper theory to estimate the geometry. We find the point group using the flow chart. Find the symmetry of those wave functions, and that would be the arrows. So we did the dance moves with the water, you know, the dipole moments in the x direction as it changes, then that's going to be the symmetry of x. We find that in the character table. And then we can figure out what type of spectroscopic interaction we have. So if it's direct absorption or emission of light, it could be X, Y, or Z, because you can put, in 3 dimensions, you could put that oscillating dipole along the Z axis. We have polarized light. And so if you use polarized light along the Z axis, then it would have the symmetry of Z. If you have polarized light along the X axis, it would be X, or Y, it would be Y. So there's 3 types of light that we could use for direct absorption or emission. Emission, the molecule drops down and spits out a polarized photon of light. And so it's the same calculation from our perspective, but different phenomena. Absorption or emission are essentially the same. It's just one's coming in, the other's going out. For scattering, though, we have 2 photons of light. They could come in the x-axis and leave on the x-axis, so that would be x squared. So both polarizations are in the x direction, or the z direction, or the y direction. And then you could also have combinations. It could come in, it's a scattering phenomenon, the photon could come in polarized on the x-axis and then bounce off the molecule and leave polarized on the y-axis. Kind of makes sense, right? You've got all the combinations of your different axes. And so they could come in on y and leave on z, come in on x and leave on y, and so on. So all of the order 2 polynomials, you know, x squared, y squared, z squared, xy, xz, and yz are your scattering phenomena. And then we would use the direct product table to connect those wave functions and then the phenomenon you're talking about. So let's do it. Let's go back to the particle in a 1D box just to remember this. We only have one axis. and we only have E and I symmetry elements. E is the identity, which is the do-nothing operator, and I is the inversion. And so we can look up here, we can see, if we invert this, we get +1. If we invert this, we get -1 because the left side becomes negative, the right side becomes positive. And so we could label these energy levels with AU if it's odd or AG if it's even. And then we have X, the polarization of, we only have, in this case, one dimension. So we could only have X polarized light. And X polarized light is AU. So over here we have this transition dipole moment squared, which is proportional to intensity. It will tell us how strong that peak is. And now we substitute the wave functions and X with these Millikan notations. So last time when we said we've got to figure out the Millikan notations, this is why. Because we have that Dirac notation for that integral, and we're going to take out the wave functions and put in the symmetries. So our question is, can we make this jump from 1 to 2? And so here's where we substitute the symmetries. So the symmetry for wave function 1 is AG. The symmetry for wave function 2 is AU. The symmetry for light is AU. So it's color-coded for you. And then we use the direct product table to come up with the results of these direct products. So we don't have to go into our character table and say, what is this row times that row? You could if you wanted to prove it to yourself, but if you take AU times AU, you get AG. Now if you look up here, this is easy. AU times AU gives you +1 times +1 gives you 1. -1 times -1 gives you +1. So AU times AU gives AG. So that's what's going on in the direct product table. This one's easy. We go look at benzene. Okay, or C3B, it's also tricky. But we use this direct product table to simplify this. And so AU times AG is AU. So AU, let's see, we do this one. AU times AG is AU. So that's where this came from. And then we do the next two. AU times AU gives AG. And that's the top row of our character table. So that means that integral is going to be not equal to 0. It doesn't tell us how intense it is, but it at least tells us this is an allowed transition. You've got to go do your math if you want to know how strong the peak is. And we're going to do that in Excel in a couple of weeks. Okay, so we can say that the 1 to 2 transition is allowed by symmetry because the thing that we're integrating is even. And the integral of an even function is non-zero. I'll pause there. Is anybody confused about anything, or if the symbols, if you want clarification on anything? Because this is such an important process. We're going to do this over and over again. So I want to make sure that you're with me. Yes?
So if it's not in the top tier row, is it forbidden?
Yes. Yeah. In the next case, we only have 2 rows. So if it shows up AU, it's forbidden. But for like ammonia, there's 3 rows. And so it could be any of the bottom 2, it would be forbidden. But if it ends up being the top one, you're good. And for water, there's 4 rows, and we'll do water today. So can we generalize? If all AG to AU are allowed, then we can go from AG to AU here, and we can go from this AG to that AU. So this is a delta N plus 1, that's a delta N plus 1. And honestly, if we swap left and right in that thing, it's going to be allowed as well too. So we could go AU to AG. So this can tell us that all the 1, 3, 5s are allowed. So we got our selection rules just from using symmetry. What is this +3? So this would be AG all the way up here to level 4, and that's AU, so that's allowed. But let's prove to ourselves that AG to AG is forbidden by symmetry. So let's check that one. Okay. Actually, this is a repeat. So let me go to the next slide. I don't know what I feel like. Okay, so yeah, I guess I just didn't change the subscripts on that. I should have gone to AG to AG. So that's kind of a mistake. I mean, there's nothing wrong on here, but mentally I wanted to go on to do AG to AG, and I didn't do that. So let's go to scattering. Okay. So scattering uses the 2 photons, and we only have 1 dimension, so it's got to be x squared. So a photon coming in, x polarized, and leaving, x polarized. So the way scattering works is it's more efficient if the incoming photon does not actually hit one of these levels. So we draw this little dashed line, and we call that a virtual level. It's not an energy level. But you'll see why we draw that here in a second. So light comes in, x squared. You have an incoming photon here, and it's not matching any of the other transitions, so it's not absorbed. It's just bouncing off the molecule, or the particle in a box in this case. And then it might be able to leave with this photon of light where it matches, the difference matches an energy level difference. So this is what they call inelastic scattering. What do you think I mean by inelastic? Some energy loss. And in fact, there could be even energy gain. If I started up here, let's say I had an excited molecule, and it went up and then dropped to the ground state, it would have an energy gain. So a photon hits the molecule, and then a blue shifted photon comes out. So you could have inelastic scattering that is energy loss or energy gain. If the molecule's already excited, it can relax and give extra energy to the photon. So that's pretty cool. That's called Stokes and anti-Stokes Raman scattering. So this is the incoming light and the scattered light, and that would be x squared. So what are the selection rules? Is this possible going from n equals 1 to n equals 2? So we have a different transition moment integral, but the piece in the middle is x squared. We still have our wave function 1 and wave function 2, so that hasn't changed. Yes?
So the energy lost or energy gained is lost or gained by the photon?
Yes. So that's the inelastic part. The photon comes out with different energy, either less or greater. Just like most of the time in like mechanics or physics, billiard balls, you assume they're elastic collisions. So the cue ball hits another ball, and you can kind of see that the momentum is transferred, and they are elastic collisions because the balls are really hard and they preserve their energy. And then it's the felt of the table that slows things down, the friction of the table. And we can kind of think of light interacting with particles that way, where a photon comes in, hits, and leaves with less or greater energy. That was inelastic. That was some energy transfer happened. And we can actually see that there's, using wave mechanics, that we can explain that and why it's quantized. Okay. So here's the ground state wave function 1, the excited state wave function 2, and then x squared is in the middle. That's that scattering operator. We would call it the polarizability operator. Because most of this Raman effect happens with visible light. So we're dealing with the polarizability of the molecule. Now in this case, we just have a single particle in a box, but when we do molecular Raman spectroscopy, we're shaking that electron cloud with the electric field of light. So let's go ahead and substitute our symmetries. Wave function 1 is AG, wave function 2 is AU, and x squared up here in the table is AG. So AG is in the middle. At this point, eventually you're going to get comfortable with this, and you'll be able to see I've got all evens and one odd, and that odd guy is going to ruin the party. Okay, because let's just do our multiplications. So AG times AG is right here, and that's going to give us AG, and then AG times AU is going to be AU. If this will work. Okay, so AU. So the integral of an odd function is 0. And so then we're going to have a forbidden transition. That doesn't mean that scattering is not allowed, but it's not allowed from 1 to 2. Yes?
Even squared? Because there's a square there?
It's the integral first and then squared. Yeah, so the integral will be 0, so the result will be 0 squared. But that's very good, yes. So the square, you might think, oh, AU times AU, because AU squared would be even, but that squares on the outside of the integral. So you would calculate that integral first, you'd get a 0 result, and then square it. Yeah, that's great. Good observation. Now, what what kind of scattering would be allowed? Probably AG to AG. Okay, so it'd go from here, it would bounce off the molecule and leave the molecule up here and n equals 3, and then we would get rid of that little poison odd function. Okay. So if the final state is AG, this is going to be non-zero, and so we just need to find a wave function that match. So AG on the right and AG on the left, that would connect 1 to 3. Does everybody see that? Yeah. And so it would also connect 2 to 4, because you'd have AU on the left and AU on the right, and the AUs would cancel each other. So for scattering, as long as the states match, AU to AU or AG to AG, it would be allowed. And notice that the ground state back down to the ground state would be allowed. So AG to AG, and that would be elastic scattering. So this 0, this delta n equals 0, would be Rayleigh scattering, which is elastic scattering. And then, so that's a picture of Rayleigh scattering. And then the inelastic Raman scattering would be this one up here. So incident light comes in, and the Raman scattered photon has this energy. The Rayleigh scattering energy photon has the same energy as the incoming light. That's why it's elastic. So how would we detect Rayleigh scattering if it has the same frequency as the incident light?
Could change direction.
That's it. It's scattering. It's bouncing off. It's got a different direction. If it's the same direction, you can't tell that anything happened. And so we would just call that refractive index. Light slows down in the medium, and if you're on the other side, you're like, wow, that light's a lot slower. It's sort of scattering or bouncing off the particles it's going through, but it maintains its same direction, so it's slowing down. And so this has a time element to it. This interaction has some small amount of time. It slows the photons down, and that's the reason for refractive index. And that's why, you can see over a hot stove or something, the sort of the wavy background. That's light traveling through air, and the air has a different refractive index because it's a different density, because it's hot and cold, and you have these currents, and that's what you're seeing, light being bent. It's that refractive index effect. You also, if you have small particles, you'll see light getting bounced off at different angles. Now, it's really hard to detect Rayleigh scattering without a really bright source of light, and so that's why we use lasers. And so we have this laser. The red light is coming at the board and bouncing off at different angles. If I match the angle, that's the specular reflectance, but all other angles are diffuse reflectance, and because the wavelength of light isn't shifting, it's Rayleigh scattering. So what you're looking at is Rayleigh scattering with the laser. Now, if I were to get a really sensitive detector and turn the room lights out, I might be able to detect from this laser hitting that dye molecule some Raman peaks coming off. And it's more probable to, at room temperature, to have the inelastic scattering where the photons lose energy. So I would need a detector that detects infrared light. So I'm using a red laser, and I need longer wavelengths, lower energy light, and I would see the Raman effect. So the advent of lasers has really helped Raman spectroscopy become useful. Before it was lasers were big and bulky and water cooled. The power supply for the laser that I had in graduate school was about half the size of that lecture bench. So it was enormous. It had a lot of pumps in it. It had some capacitors to drive these flash lamps to get the power up so it would have a bright laser light. And those capacitors looked like half-gallon milk cartons. And they said on the side, caution, lethal dose. Or lethal dose of electricity, essentially. Because if you were to get that many coulombs in your body, it would kill you. So, whenever we were to do maintenance on that cabinet, you had to ground out the capacitors. because you didn't want to be in there. Everything's at high voltage. Even if it's unplugged, the capacitors are still charged up. So you have to ground them out. And this is what we always did for the new grad students. It was my turn when I was new, and then we passed it on down. You have a big, long screwdriver, and you stick it in there and ground them out. It sounded like a 22, like pow! And the end of the screwdriver was all melted off. So, yeah. Yeah, so that's how much electricity it was. And so you sit there and pow! And everybody cheers. And you're like, okay, it wasn't so bad. It's a little bit of hazing. So let's do now direct product tables and this calculation with a three-dimensional molecule, a different character table, so on. You know, last time we kind of worked on assigning Millikan notations to different orbitals, and this is ammonia. And so in this particular molecular orbital for ammonia, you kind of have those non-bonded electrons on top of the nitrogen, kind of in phase with the 1s orbitals on the hydrogens. And so, or maybe out of phase, so that the electron cloud's expanding into those lone pairs while the 1s orbitals shrink, and sometime later the 1s orbitals expand while the lone pairs shrink. And so you have this oscillation in the electron cloud, and that's the symmetry axis of ammonia, so that's the z-axis. So that oscillation has the same symmetry as z in the character table. So you find z, come over to the left, that's A1. The one on the top is a little more difficult to see, but it's symmetric all around the molecule, top and bottom, left and right, etc. And so it's also going to be totally symmetric. It's going to be top row. So the top one will be a little more tricky to assign the symmetry. And then we need to ask the question, is this HOMO to LUMO transition allowed for ammonia with light? So direct absorption or Raman. I think we're just doing direct absorption on this slide. So Z polarized light would be A1, and X or Y polarized light would be E. So we have two calculations to do because we really have two types of light, either X or Y polarized or Z polarized. Yes?
What does that E mean?
It's this row here on the character table. And it's a what we call a two-dimensional row, because in anything that is threefold symmetric or higher, the X and the Y coordinates can't be reduced to individual like X or Y. They're essentially the same. And if you think about a physical object that has threefold symmetry or fourfold symmetry, fivefold, if you put it, I'm trying to think of the best way to illustrate this. It's the moments of inertia are the same around the X or the Y. One way to know that is if you push it to the edge of the table, it doesn't matter if one hydrogen is leaning off the table or two coming off the table. They have the same tiltingness. It's the moment of inertia that we're talking about. It's a little more difficult when you flip it to kind of keep track of what's going on. But if you push two hydrogens off the table, it'll tilt right at the center of mass, just like if you push one. Okay, for water, it's obviously not the case, right? Water is an asymmetric molecule, so X and Y are totally different. But for a threefold molecule, symmetry or higher, you have X and Y being the same, and they can't be reduced any further. And so that's why we have a doubly degenerate Millikan notation row in a C3V molecule, or like a D4H, where you have 4, N equals 4. For a fivefold molecule like cyclopentadienyl anion, it's a D5H, also X and Y are coupled. Now the weird one is methane. It's tetrahedral, and it's really kind of like a sphere, even though it's a tetrahedron, and you can't separate X, Y, or Z. And so instead of an E row, it's got a T, and it's threefold, because X, Y, and Z can't be reduced even further. Okay. So that's where that E comes from, and that E is different than this E. This is the identity operation, okay, and that's just the do-nothing operator, okay. And this E is a Millikan notation. So whenever we're labeling wave functions or labeling light, we're always picking a row in the character table. So when you see E for XY polarized light, you see this E right here, it's this row in the character table. And when you get to the direct product tables, it will be in those direct product tables as well. So this is the question. Does this integral equal 0? We're going from the HOMO to the LUMO using light, or if it's emission, the reverse. So you find the Millikan notation for that. Now, do y'all remember what this stands for? This is highest occupied molecular orbital. Yes. So this one has electrons in it. This is the lowest unoccupied molecular orbital. So this one is empty. And we're asking, can light cause the electron to jump from this orbital to that orbital? And so the symmetry of the occupied orbital is A1. The symmetry of light is A1 if we have Z polarized light. And the symmetry of the LUMO is A1. So that looks pretty good because I've got A1 times A1 and A1 times A1. So everything's even, everything's top row. That one's going to be allowed. But this one, we don't know. We'll have to use the direct product tables for that. So let's go through these. Here's the direct product table for all of these point groups. And so you have for C3V or D3 or D3D or D3H. And then here's your 3 Millikan notation, your 3 rows in those character tables. And the these 3 rows times 3 rows. And these are all of the multiplications. So let's do this one for X polarized light. And so E times A1. So we find over here, this is E times A1 gives us E. Everybody follow that? That was pretty easy, okay? And then we have A1 times E. So same kind of thing, A1 times E gives E. So our result of this direct products is going to be E. So now we have the integral of E. That's not a top row. Okay. So the result of the direct product is E, therefore the transition dipole moment integral for this is going to be 0. So for XY polarized light, this is forbidden. The transition for Z polarized light is allowed because it's A1 times A1, which gives A1, and A1 times A1 again gives A1, so the result is A1, therefore it's not equal to 0. So what we did for the one-dimensional particle in a box is really no more difficult, this is no more difficult than the one-dimensional case. We just have a different character table, different direct product table. Did you have a question?
Yeah, I was gonna ask how we assign the wave function. One was A1 and the X is, I got how X is A1, I think. But how did we assign the wave functions A1?
Yes. So for this picture of these wave functions, yeah, let's practice that. So how we get these is the real question, because if you have those wrong, then the problem's wrong. So let's work with, I think I've got water on here too. Here's some rotational levels. Let me make a point here about the rotational levels, and then we'll get to designing those wave functions. The particle in a box alternated, the vibrational energies alternate, and so do the rotational energies. So for the rotation, it starts with J equals 0, that's the quantum number J. And it starts out as top row, and then whatever the symmetry of that rotation is, and then top row, and then the symmetry, and then top row. So how do I know the symmetries of these rotations? That's where that R sub X, R sub Y, and R sub Z come in. And so we can look at those, like the rotation for RY and H2O are shown to the right. So this B1 is where, in the character table for water, RY is on that row. And so you say, if water's rotating around the y-axis, I go to the character table, find RY, and come across, and I'll see B1. That doesn't mean all the energy levels are B1. That just means the ones that have odd quantum numbers are B1. The even quantum numbers are A1. So it goes top row, symmetry of the motion, top row, symmetry of the motion. So here's the rotation around Y. It's B1. We find it in the character table. There you go. And then here's the direct product table. And just to show the point, I've filled out the other 6 squares just to show that it's symmetric. The ones you get, the ones we have in your packet are all triangular. So can this rotational mode be excited by direct absorption of light? It's the C2V molecule, so here's the character table. The even quantum numbers are A1, the odd quantum numbers are B1. For rotation around X is B2, rotation around Z is A2. So you could do this for the other rotations too. So let's just look at rotation around Y. The symmetry of Z, we find that in the character table, and it's A1. So A1 times A1 is A1, and then A1 times B1 is B1. Notice that this is a trend that you can recognize. Any of these rows, A1, A2, B1, and B2, times A1 here, notice how all of these match. So essentially anything times A1, you get that back. Because A1 is symmetric, so it's like anything times plus 1 is that thing. And so this one on the right, after a few times with this, you'll be able to do that one on the right without even having the direct product table. Because you have anything times A1 is returned. So A1 times A1 is A1, and B1 times A1 is B1. Then we can do rotation around, I think that one was X. The vibrational energy levels, we have the same kind of alternating pattern. This is for the asymmetric stretch. Notice that it's top row and then the symmetry of the stretch, and then top row, the symmetry of the stretch. So that's how these energy levels are labeled. The only real weird one is electronic wave functions, these green and red diagrams where you can't depend upon the ground state being A1. Okay. For vibration and rotation, the ground state is always even, and then the next state is whatever the symmetry of the motion is. And so let's look at this asymmetric stretch. Here's the whole problem shown. So that asymmetric stretch is B2. It's right here. If we have Y polarized light, that's also B2. So we have A1 times B2 is B2, and then B2 times itself is A1. So this stretch can be excited by Y polarized light. It can't be excited with Z polarized light. So Z polarized light comes in, interacts with the ground state, and that can't cause a transition to the Y vibrational state because the result is B2. Yes?
When you set it up, is it always going to be odd times the direction of light times even? Or what? The B2 to A1.
Yeah, so if we're starting in the ground state, then that'll be A1 or top row for that ground state, okay, for vibration. But what if I told you we're going from V equals 1 to V equals 3? So if I give you, you'll need to, I guess I'm trying to say you'll need to know this diagram. Because if I'm going from here to there, then it's B2 to B2. You see?
Yeah.
Yeah.
Why did you have Y?
Okay, so then that's the polarization of light. The thing in the middle is always light.
Yeah. But it was Y times Z times A.
Oh, okay. It was this Y here. That's the motion of the molecule for vibration. So that motion has Y symmetry because the dipole is oscillating in the Y direction.
Okay.
So we did those with the arrows, and we tried to decide, does this look like Y or does it look like Z? So this one, where they're stretching symmetrically, the dipole moment was changing in Z. So you could say, oh, it has Z symmetry. And so when we talk about X, Y, and Z, we're really just identifying the symmetry of that wave function. So wave function is really complex, and we're simplifying it to say it looks like Y, or it looks like X, or it looks like Z. And then light, also with this oscillating dipole, is going to either be in the X, Y, or Z direction. So that's why I have two Y's there. And in that one over to the left, I have Y and Z. That Y on the left is the vibrational motion. And then that Z is light. And then that A1 is ground state.
So when you do vibration, it's always going to be the direction of
Yeah.
vibration.
Yeah, and what will happen is because you're starting in the ground state, Y will match Y. So Y light will match a Y motion. And Z light will match a Z motion, and X light will match an X motion. Yeah. So if you identify what the motion looks like, then you automatically know what kind of light will excite it, because you're starting in an even state. And so that's why a lot of times people label this IR. They're saying if the motion is Z, then light in the Z direction will excite it. And if the motion is X, then light in the X direction will excite it. Let's do a Kahoot on identifying the Millikan rotations, because that's the skill that we need. We have just enough time. It's just a 4-question Kahoot. It's just some practice. Three more. One more. All right, let's go. So the symmetric stretch in formaldehyde. You may need your character tables. Let me draw it up here real quick.
Well, we don't got a lot of time, so I might as well just put in the answers.
Yeah.
Oh,
Good job, number 11.
wow.
Yeah. All right, so yeah. The asymmetric stretch of formaldehyde. So here's the 4 rows in the character table, and here's your different symmetries. If I've done it right from memory, I'm a little nervous. But I just saw it on like 4 slides ago. I haven't told you the coordinate system, but I'm hoping that you can figure that out. This is a C2V molecule. Yep, and the symmetry axis is going up and down, so that's Z. So X is coming out at you and Y is going to the left. So it should be Y symmetry, V2. Now let's make things a little more interesting. Let's go to the wave function. So that's the wave function for one of the electronic molecular orbitals. And so you're looking at that picture of the red and greens, and you're trying to say, is it Z, X, or Y? So how is it changing? Remember, those are oscillations. So is it oscillating in the X direction, oscillating in the Y direction, or oscillating in the Z direction? X is coming out at you. Y is going this way, and Z is going up. All right, pretty good. The picture, it's oscillating up and down. Okay. One more, and we'll be done. Make your choice. Yay! Oscillating in the Y direction, left and right. So here's the picture again. So if the red is shrinking and the green's expanding, and sometime later the green will shrink and the red will expand. So it's doing this. And that's left and right. So that's the Y direction. Yes?
If you look at a picture like that, how would it look if it oscillated on the x-axis?
You would draw it like this. So you would draw a big cloud like that, and then behind it, you draw a cloud like that. So this might be unshaded and shaded behind it.
Okay,
So that would be the P, the pi bond in that molecule would oscillate in the x direction. Can you see that? Beautiful drawing.